Okay, I'm looking at the unit practice test for Chapter 11. So first thing, notice all the information that you're going to be given on the test. So you have all your standard pressures over here. This implies that, that the 273 is the standard temperature, so you should know that and how to convert. We have a couple things here about partial pressures. This is Graham's law of diffusion about the speeds of particles. The gas laws, they're given here as P1 V1 over T1 equals P2 V2 over T2, and realize that the three different gas laws are special cases of that. The ideal gas law, the constant R, and then a couple of simple formulas to remind you about density and molar mass. So the first question over here, these are the true-false questions. So we're saying a balloon occupies a greater volume at room temperature than at STP. Okay, a balloon occupies a greater volume at room temperature than at STP. So that's kind of assuming that you know that room temperature is usually about 20 degrees to 25 degrees. And that at STP is 0 degrees Celsius or 273. Okay, and so a balloon occupies a greater volume at room temperature. Yeah, if it's going to be warmer, then it's definitely going to be larger. Okay, assuming that the temperature is constant. Now, at constant pressure, volume and temperature are directly related. So that's true. At constant pressure, okay, the volume and the temperature are directly, if temperature goes up, okay, then the volume also goes up at constant pressure. So that means that this would be a true statement if we're assuming that the pressure, okay, in the room and the pressure at STP are the same, which I don't think they really are. So I would actually call this TT, but we have it marked as a TTCE, true, and an explanation. Because, I think it doesn't quite work here because, it's not really constant pressure from STP to room temperature. Okay, number 2, at 15 degrees, the average speed of methane is the same as that of oxygen. Absolutely not. Okay, that's definitely a false statement. Okay, the particles do not have the same mass, and so therefore they're not going to have the same speed. Now, CH4 and O2 have the same average kinetic energy at 15 degrees. That is true. And average kinetic energy is 1/2 mv squared. And that can be the same for both because the one with a larger mass has a lower velocity and vice versa. So there's a false and a true. Third one, when a sample of nitrogen in a rigid container is heated from 30 to 60, the pressure of the gas increases. That is true. Okay, it does not double, but it definitely increases. When the temperature increases, gas molecules move faster and collide with the walls of the container harder and more frequently. That is absolutely true, and that is the reason why the pressure does increase. So I would call this true with the correct explanation. Okay, ACE. That'd be a great answer. Okay, looking at 4. 745 millimeters corresponds to how many atmospheres? So we're just going to set that up as 745 millimeters of mercury. And then we're going to multiply by a conversion, which would say 760 millimeters of mercury. And we're trying to get to atmospheres, so 1 atmosphere, and that'll come out to be 0.980. And we got these two numbers here from way up here, where we're given all the values at standard pressure. Okay, standard temperature and pressure. Okay, that is just knowing your numbers there. So 760 millimeters of mercury, or it could have been 1 atmosphere or 101.3 kPas. The numbers at the top of the page. 0 degrees Celsius or 273 Kelvin. That is standard pressure. So this is kind of a memory question. Number 6, which of these is not correct under the kinetic molecular theory? And we really ought to say the kinetic molecular theory for ideal gases. Now you can go back to the notes and look things over. And we're saying that, kinetic molecular theory, A, B, and C are all true. The particles are moving all the time. Okay, pressure has to do with the number of collisions with the walls of the container. Okay, the particles take up the volume of their container. But it is not true for an ideal gas that they have any kind of attractive forces. We're saying that the particles are completely independent, do not attract each other. So this is the answer D is the part that is not correct under the kinetic molecular theory. Number 7, according to kinetic molecular theory, which observation is not correctly explained? So let's look at the answers. Decreased volume of a gas results in increased pressure. So if you decrease the volume, it increases the pressure. That's true. Why? Because more particles in an area have more collisions with the walls. Okay, more particles. Oh, which one is not correctly? Because I was about to say, well, no, that's true. That's fine. More particles, more collisions in there because if you decrease the volume, you're going to get more collisions. So actually A is good, and that's why it's not the answer. Okay, B, increased temperature of gas results in increased volume. Okay, that's true. Particles move faster, colliding more often and harder with the walls. Okay, so collision with the walls, that's talking about pressure. Okay, and here they're talking about volume, so that's why this one is the answer. It's a true statement, but it's not relevant to explaining volume. So that's why answer B is correct. C, increased temperature of a gas results in increased pressure. Particles move faster, colliding more often with the walls of the container. Okay, so that one is a fine answer, and all three are correct. That is not true. So B, okay, has correct statements, but they're talking about pressure, not volume. Number 8, the graph above shows a relationship between which set of gas properties? Well, we should know that this is directly related. So we're saying for, property X and property Y, okay, when one goes up, the other goes up. When one goes down, the other goes down. So that is not pressure and volume. Pressure and volume, one goes up, one goes down. Volume and temperature and pressure and temperature, they are both good. So a graph would work for that one. So the answer is 2 and 3 only. Answer C. Number 9, in which sample do gas molecules have the greatest velocity? Okay, greatest velocity. These are all the same volume, so that's not it. Okay, greatest velocity, we have temperatures, and we can see that we have different kinds of molecules. So we know that the higher temperature is the one we want because the particles go faster, and we have the lightweight particles and heavier particles, and the lightweight particles are the ones that are going to be moving the fastest. So we have two factors, temperature and the mass of the particles. Number 10, in a sample the gas at 12 degrees is heated so its total kinetic energy doubles. What is the new temperature of the sample? Okay, so we kind of say, well, temperature is a measure of the average kinetic energy, but only if we are working in Kelvin. Okay, so 12 degrees to 24 degrees, that is definitely not the answer. That's a kind of a sucker answer there. Don't go for that. What you have to do is you have to take 12 degrees, and then you add 273, and we can see that's going to be 285. And then if we want to double that, then we are going to have, that'll be 570 Kelvin, and we don't want to pick that one because that's not Celsius, that's Kelvin. Okay, and then we have to subtract 273, and there's where we get back to the 297. So you have to take your number here, 12, add 273, then double the answer, and then subtract 273, and that'll give you the correct answer. Okay, we're talking about 11 and 12 is a 1-liter balloon at 30 degrees, contains 0.3 moles of hydrogen and 0.01 moles of helium. Okay, so we have two different gases inside there. So what's the total pressure of the balloon if the partial pressure of helium is 0.25? Well, every gas particle causes the same pressure. So if 0.01 moles of helium causes 0.25, then 0.03 moles of hydrogen must cause 3 times that much, so it would cause 0.75 atmospheres. And if we add those together, we get 1 atmosphere. So the number of particles is related to the pressure it exerts. Number 12, after 2 days, which gas has probably leaked the most? Okay, the particle that is moving the fastest is going to leak the most. Okay, who's going to go the fastest? Hydrogen and helium. Hydrogen weighs 2, helium weighs 4. Hydrogen moves faster, so that's the one that's going to leak out the most. Getting to 13. A container is filled with 5 grams of methane, 5 grams of C2H6, which is ethane, and 5 grams of C3H8. which is propane. Which gas has the greatest partial pressure in the container? Now, so we say that particles all cause the same pressure. They can all cause the same pressure, particle by particle. So the more particles we have, the more the partial pressure is going to be for that chemical. So 5 grams, 5 grams, and 5 grams, we have to change them all to moles. So CH4 weighs less than C2H6 or C3H8. So this one is going to give us the most moles. So that's why it's going to have the greatest partial pressure. Number 14, a balloon is inflated with oxygen gas at 15 degrees to a volume of 1.2. If the temperature is increased to 25 at constant pressure, then what's going to happen? Okay, well, 15 and 25, if we actually want a number, we're going to change those to Kelvin, but we're just kind of doing a general idea here. So as you warm this up, okay, then the volume of the balloon is going to increase. Okay, now notice this is constant pressure. So you just have a balloon out in the normal pressure. If you warm it up, it's going to get larger and larger and larger. Okay, a cylinder containing CO2 gas has a piston that can move up and down freely. If the volume of the piston is increased from 1.1 to 1.3 at constant temperature, which is true. Okay, so we are going to increase the volume, so therefore the pressure is going to be a little bit less. Now this is because the temperature is not being allowed to change. So we're looking for something where the pressure is going to be less. So the gas molecules hit the walls less frequently. Yes, that's going to be the reason why the pressure drops. So that's going to be true. The gas molecules hit more frequently? No, they're going to hit less frequently. The gas molecules move more rapidly? No. Okay, at the same temperature, the same particles are going to move the same speed, and the same thing here about more slowly. So it's going to have to be answer A. They hit the walls less frequently, which is why the pressure is going to drop. For 16, a rigid container, that means volume is constant, okay, contains 0.6 moles of xenon gas at 50. If the temperature is lowered to 20, which of the following is also decreased? So we're cooling it down. So the pressure of the sample, yes. Okay, so if you have a gas and you cool it down, the pressure is definitely going to be decreased because they're going to hit the walls of the container less often. The average speed at which the gas molecules travel, that's a yes. Okay, because the temperature is a measure of their kinetic energy, which is going to be a measure of their speed if we're talking about just one gas. And the number of collisions the gas particles make with the walls of the container, that's also going to be true, because if they're moving more slowly, they're not going to hit the walls quite as often. So it's answer 1, 2, and 3. All three of those are good answers. 17. A gas at 750 millimeters of mercury with a volume of 2 liters is allowed to change its volume at constant temperature until the pressure is 600 millimeters. What's the new volume? Okay, so we're saying here is a pressure, and here's a volume. Here's a new pressure. So what's going to happen to the volume? So we know that as the pressure decreases, then we know that the volume is going to increase. And we just have to put this into P1 V1 equals P2 V2. And if we just substitute those four values, they're both millimeters of mercury, so that's fine. We're going to get 2.5 liters. So that's just a substitute into the Boyle's law equation. 18. The sample of gas occupies 324 milliliters at 40 degrees. What volume will the gas occupy at 20 degrees if there's no change in pressure? Okay, so we're going from 40 down to 20. So it looks like it might go down to half, okay, which would be 162. That's not the answer because we haven't changed to Kelvin. So what we're going to do is we have two temperatures and we have a volume. So this is going to go into the V1 over T1 equals V2 over T2. But when we use these numbers, we're going to say 20 degrees is 293 Kelvin, and 40 degrees is 313 Kelvin. And so we're going to put those two numbers in. So 324 over 313 equals X over 293, and we're going to get 303 milliliters. So We know it's not 162, okay? 324 is going to be a little bit smaller, so it's not going to be 346 or 648. So we can eliminate those even without doing the math. 19, what would be the pressure of a gas originally at 101.3 kPa if the temperature is lowered from 95 to 85? So this is a similar problem. Again, we have P1 over T1 equals P2 over T2. And again, you know, we can't use 95 and 85. We're going to have to put those into Kelvin before we substitute them in. And it's going to be a little bit less. Now, all our answers are millimeters of mercury. So we're going to change this. We're going to use 760 millimeters of mercury as our P1. And we see it's going to drop down just a little bit. Okay, just a little bit. So we can eliminate 781 because that's going up. Okay, 680, 70, 735, 739. You know, they're all possible answers. You know, it looks like you need to go down just a little teeny bit once you add 273. And we're going to get to 739. So you can work that one out. Again, be sure and change your temperatures to Kelvin. These temperatures are going to turn out to be 368 Kelvin and 358 Kelvin. And this number up here is 760. So when you work that out, we get to 739.3, but that'd be 739 millimeters of mercury. So be sure and change to Kelvin. 20. At a gas at 20 degrees and 680 mmHg occupies 345 milliliters. What will be the volume at STP? Okay, so this is going to be a P1V1 over T1 equals P2V2 over T2. Okay, and we can see that 25, we're going to have to change that to 298 Kelvin. Okay, 680 milliliters is fine, 345 milliliters is fine, so that's going to give our P1, V1, and T1. But the STP, okay, STP implies two numbers. So it implies that the pressure is, you know, 1 atmosphere, or in this case 760. So this isn't going to be 760 millimeters of mercury, and the temperature is 273 Kelvin. So we're going to try to find the second volume. So we have three numbers to place in here, and then these two are implied. So we have 760 and we have 273, and when we get all done, we get 283 milliliters. So I'll leave that for you to actually calculate. But remember, STP implies a temperature and a pressure. Okay, so for 21, a sample of chlorine is placed in a piston in a cylinder and is allowed to move freely. The sample originally has a pressure of 85 kPa, temperature of 12 degrees, and a volume of 0.60 liters. So find the volume of find the pressure of the sample if the temperature is raised to 30, okay, and the volume is fixed. So all we're changing is temperature, and we're looking at the pressure. So this is P1 T over T1 equals P2 over T2. Remember that these have to be changed to Kelvin. So the temperatures you can see here are 285 and 303. And then we just substitute it in. We can go ahead and leave things in kPas. And when we get all done substituting and calculating, we get 90.4 kilopascals. So make sure you change your temperatures to Kelvin and substitute carefully, and you'll be okay. You have letter B, a temperature is held at 12 degrees. What's the pressure of the sample is allowed to increase to 1.2 liters. So we're starting with 12, we're ending with 12, so we don't even need to worry about that. We're talking about volume and pressure, and so we know that the equation here is P1V1 equals P2V2. Okay, we have our original pressure from the problem. Okay, we're trying to find the new pressure. The original volume was 0.6 liters. And we're saying we're going to double that. So if we're going to double the volume, the pressure is going to go down to 1/2. Half of 85 is 42.5 kilopascals. And that seems pretty simple. For C, find the volume of the gas if the conditions were adjusted to STP. So we saw that just a moment ago. So we are going to do PV over T equals PV over T. Okay, pressure 1, that's given in the problem. Volume 1 is given in the problem. Temperature 1, we change to Kelvin, that's given in the problem. But for the for the P1, V1, and T1, we're looking for V2. Pressure 2 is STP standard pressure, and that's going to be 101.3 kPas. We have to match the units from the given problem, and the temperature is going to be 273 Kelvin. So we just substitute all the numbers in to this expression. We're going to solve for V2, and it comes out to be 0.482 liters. And again, we're not really worried about significant figures here. Okay, 22. A 0.8 liter plastic container is filled with SO2 gas with a pressure of 500 torr at 30 degrees. Okay, so if we're going to do anything with that, we're going to change that, add 273 and get 303 Kelvin. Calculate the number of moles. Okay, so as soon as we see moles, we know this is a PV equals nRT problem. So pressure, okay, we have to be in atmospheres because we're going to use the value of R, and R is liters, atmospheres, moles, and Kelvin. So change our 500 torr to atmospheres, where our volume is going to have to be in liters, and it is in liters, so that's good. Temperatures in Kelvin, that's good. And so the only one we don't know, I mean, we do know the value of R, that's 0.0821. So we're going to find moles. And we're looking for moles, that's easy, so we just substitute in, evaluate, and we get the answer here. Number of moles, 0.0212 moles. So again, you have to change the atmospheres, and liters was okay in Kelvin. Find the density of the sample. Well, we just know that density is mass over volume. Okay, so we say, well, if we knew the mass, we'd be good, but we can do the mass because we have to remember way back from a long time ago. If we know how many moles and we know what chemical it is, it's SO2. So we'll take an S plus 2 O's and we get 64.06 grams per mole. So we use that as a conversion. So we have 1.36 grams. So density is mass over volume. The volume was given in the problem, okay, way up in the beginning. We know the mass, divide those two, and we get the answer, 1.69 grams per liter. And that's our answer. Okay, 23. A mixture contains 0.2 moles of NO, 0.8 moles of NO2, and 0.6 moles of N2O4. The total pressure of the gas is 3.2 atmospheres. So calculate the partial pressure of the NO2. Now this is not difficult as long as we don't get too confused. So the idea is every gas has the same power to cause pressure. So if we were to take all three of those gases and add them up, we find out that we get 1.6 moles of total gas inside there. So if 1.6 moles will exert 3.2 atmospheres, then we want to know, well, how much will 0.8 moles, because we're doing the nitrogen, how much will that exert? So we can see that that's going to be very proportional. So we can say that 1.6 moles exerts 3.2 atmospheres. So 0.8 moles exerts X. And we can solve for X, and we see we get 1.6 atmospheres. Now, when we're talking about this mole and this mole, that's officially called the mole fraction. Okay, and that's there. So mole fraction times 3.2, it's another way. So mathematically, we're doing the same thing. If you want to substitute into the equation, which is given on the first page, we're really just doing a proportion. So 1.6 atmospheres. Now, if NO2 effuses with an average speed of 515 meters per second, find the rate of effusion of N2O4. So here's our equation, okay, and the equation is that the rate of their velocities is equal to the square root of the rate of their molar masses, but, you know, whichever one is on top here goes on bottom here, and the top here goes on the bottom here, because the mass and velocity are inversely related. So when we go back and figure out their molar masses, so NO2 is going to weigh 46, N2O4 would be double that, be 92, and so we're going to substitute in 515 meters per second for the NO2, and we're looking for the velocity of the N2O4. We put in there two masses, and notice that N2O4 is on the top here, but it's on the bottom here, and the NO2 is on the bottom here, but it's on the top here. And when you get all done, you find out that the velocity of the N204 is 364 meters per second. So it's kind of a substitute and evaluate sort of a problem. And that is the entire test.